Okay, once again, we've got a car on a lift, and this time the lift is being lowered with a constant velocity, and that's going to be critical to our understanding of how to proceed with this question, of 2.1 meters per second. So again, let's proceed like we have been in the past. Start with a free body diagram. Here's our car, just keep it simple. 900 kilogram car. Force of gravity down for sure. And there's something holding it up, and it's this hoist preventing it from falling at 9.8. The hoist is holding it up with a normal force. Now, I'm not going to put an arrowhead on it just yet. We want to know which force is winning and which one is losing so that we can proceed. This is the key. The velocity is constant. It's not changing. And don't forget, acceleration is defined as the rate of change of velocity, how quickly your velocity is changing. So if you've got a constant velocity, that means your acceleration will be 0 because your velocity is not changing. And if your acceleration is 0, that also means, according to Newton's second law, where F net is ma, if a is 0, that means your net unbalanced force must be 0. In the physics world, that means everything has to be balanced to have a net force of 0. So you can guess, our normal force should be the same size as our force of gravity. Now, it doesn't mean it's not going to stay stationary. It just means it's no longer going to accelerate. So trying to be consistent with our process, we've got our diagram, we know our net force is 0, and our second step is always this. F net is the sum of the forces that are acting on the object. Our net force in this case is 0. So it doesn't matter what we define as up or down, or positive or negative. So let's just keep Fn because it's up as positive and Fg as negative. And you can see right away that my normal force when I add Fg to both sides will be equivalent to Fg. So my normal force is just mg, which is 900 times 9.8 meters per second squared, which is 8,800 newtons.